Raw data in its native state is impenetrable to the human eye. We aren't built to process thousands of interlocking numbers at a glance. To us, it appears as a cascading wall of noise. Take a sociological survey, like the General Social Survey. Even a sample of 50 respondents answering 4 questions creates a matrix of 200 distinct data points. Or consider a typical real estate market snapshot, mapping 69 homes across 11 different characteristics. If you take this raw matrix and dump it directly into statistical software, the computer will gladly process it. But without defining what these numbers represent, the software will execute the arithmetic without providing any usable insight. To perform rigorous statistical inference, we have to establish the underlying rules governing this grid. We must translate a physical phenomenon, like a house, into a structured mathematical object. A dataset is a structured matrix that maps real-world entities into a computable format. Before you can run a single equation, every piece of information inside this matrix must be explicitly classified. This classification relies on 3 foundational pillars. First, the observational units. Second, the distinct variables. And lastly, measurement scales. Defining these 3 structural boundaries dictates whether your algorithms output actual truth or a flawed calculation. This vector diagram shows a clean 11-column matrix representing our real estate data. Every single horizontal row in this grid is an observational unit. In this case, one row represents exactly one discrete physical property for sale. Conversely, every vertical column is a variable. A variable records one distinct piece of information, like the exterior siding material, measured across all the observational units. Where they intersect is a single cell. That cell is the specific observation of one variable for one specific unit. Mapping this orthogonal relationship between the units we observe and the variables we measure is the required first step in turning the physical world into computable data. Once the grid is established, every variable must be sorted into one of 2 distinct classes. The first is qualitative, or categorical variables. These yield non-numerical classifications, like sorting a house by whether it is made of brick or wood frame. The second is quantitative variables. These yield actual numerical measurements, like the price of the home in dollars. Quantitative data then splits again. Discrete variables are strictly countable, whole values. A house can have 2 bathrooms or 3, but it cannot have a continuous fraction of a bathroom. Continuous variables, however, can theoretically take any value within a given interval. The square footage of a lot might be measured as 5,445 square feet, but conceptually, that measurement sits on a smooth sliding scale of infinite precision. Misidentifying discrete versus continuous data determines which statistical models can be validly applied to the matrix. Even within these categories, data contains varying levels of precision. We classify this using a measurement hierarchy, ranging from weak information to strong information. There is a common trap here, assuming that because data is recorded as a number, it possesses quantitative meaning. This brings us to the nominal scale, the lowest tier of the hierarchy. Nominal variables identify values merely by name or classification. The zip codes in our real estate dataset are numbers, but they serve strictly as geographic labels. Because they lack quantitative value, you cannot average 2 zip codes together to find a middle location. The math will execute, but the logic fails. The next step up is the ordinal scale. This introduces a ranking order, like rating a house's condition from 1 to 5. But the conceptual distance between a 1 and a 2 might not be the same as the distance between a 4 and a 5. The interval scale strengthens the data by introducing fixed units of measurement. Temperature in Fahrenheit is an interval variable. The degrees are consistent, but the 0 point is entirely arbitrary. 0 degrees does not mean an absence of temperature. The strongest level is the ratio scale. It possesses both fixed units and a true 0 point. The price of a house is a ratio variable. $0 means an actual absence of cost, allowing us to accurately state that a $200,000 home costs twice as much as a $100,000 home. Pinpointing a variable's exact measurement scale is the ultimate diagnostic check. It tells you exactly which mathematical operations are permissible. Proper data classification is a functional necessity for accurate computation. Let's look back at the qualitative nominal variable of exterior siding from our dataset. Because it is nominal, attempting to calculate a mean or a standard deviation for brick and wood frame is mathematically impossible. This animated graphic demonstrates the correct mathematical tool for summarizing qualitative data, the frequency distribution. A frequency distribution creates non-overlapping categories for the values, brick, frame, and other, and simply counts the number of observations that fall into each one. By properly applying the rules of its measurement scale, we transform 69 chaotic rows of text into 3 pristine, actionable data points. A computer does not know if it is performing the correct analysis. It will blindly process whatever matrix it is fed and execute a beautifully annotated, incorrect output. This is why the sequence of operations for any data professional is rigid. Define the population, map the observational units, and rigorously classify the variables. Failing this taxonomy check renders any subsequent machine learning or statistical modeling mathematically invalid. A dataset's measurement scale isn't just metadata, it is the fundamental source code of all statistical logic.